Welcome along, physics fans. Today we're going to do a Christmassy capacitor question. As you can hear, a bit of noise in the old office today. This question is from AQA 2021, paper 2, question 1. In this first part, we're asked to explain what is meant by a dielectric constant of 6. Well, we know that the capacitor formula, the area of the plates divided by the distance between the plates, epsilon 0, epsilon r. You multiply that lot together, you'll get the capacitance that you've created. Now, epsilon 0 is the permittivity of free space to measure how easy electric fields can pass through free space or the vacuum. And ER for our question here is 6. And this is the relative permittivity of, in this case, micro. Now this means that it has a value of permittivity that is 6 times higher than the value E0 or the value for free space. So ER equals 6 implies that its permittivity is 6 times E0. So mica is made up of polar molecules. Now, polar molecule is basically a sausage shape or a lemon shape with a plus at one end and a minus at the other. And the big thing about polar molecules is, well, the two big things. Firstly, they can kind of rotate around a midpoint, and they are all in totally higgledy-piggledy randomly with inside the mica when it's like this. Right? Now, I've connected up 2 plates here. The top one is positive, and we're told in the question that the capacitor is charged up and then isolated. Now, that isolated means that no charge can leave and no charge can come on. So we have a fully charged capacitor and it's not going to change. Now, I've inserted a voltmeter here, and it's an ideal voltmeter, which means it has R equal to infinite number of ohms. In other words, no current can flow through the voltmeter. In other words, no charge is going to leave. Okay, so what happens then is that when we put the mica in, we line up one of our sausage molecules. I'll do a big one like this. It's going to line up with a negative at the top and the positive at the bottom. So now imagine that you've got a whole pile of these mica molecules lined up like that. Now, just considering the mica molecules, plus at the bottom, negative at the top, they're going to create an electric field, just the mica molecules, heading upwards. Let's call that ED for dielectric, ED. But the original plates are also going to have created an electric field going downwards, which we'll just call EP. Now, ED is going to be relatively small compared to EP, but nevertheless, it's there. So what we have is 2 vectors. Electric field is a vector in opposite directions, meaning that the overall electric field between the plates reduces. This means that the voltage here will drop. And that's the key point. We know, of course, that Q equals CV, which means that the capacitance is equal to the amount of charge divided by the voltage between the plates. Well, the amount of charge is fixed. The voltage, as we've explained, has reduced. Therefore, the capacitance has increased. How do we put all that into words? Well, maybe like this. An electric field exists between the plates. The polar molecules in the mica all line up with their positive ends pointing towards the negative plate. This creates a counter-electric field to the one between the plates. This counter-electric field reduces the resultant electric field, which in turn reduces the voltage between the plates. Since Q equals CV, and we know that the charge on the plates is fixed because the plates are isolated, this means that if V drops, then C must increase. Calculate the difference between the initial energy stored by the capacitor and the energy stored when the mica is fully inserted. And I've just copied over some values. So we know the initial capacitance, we know the charge, which we know is fixed because the capacitor is isolated. We know that the new relative permittivity is 6 as well. And the formula for energy stored in the capacitor is half Q squared over C. There are other versions of that, of course, but we don't really want to get involved in having to calculate what the new voltage is going to be across the plates. So use this version. Okay, so how to proceed? Well, then we could say that the change of energy is going to be equal to a half Q squared over C final minus a half Q squared over C initial. And if you factorise that, you get that a half Q Q squared, because it's constant, 1 over the final capacitance minus 1 over the initial capacitance. So that's the formula you're going to have to use. We know Q is fixed, as I've said, so what's the final capacitance? Well, we know the formula for a capacitor in terms of its permittivity is A epsilon 0 epsilon R over D. And A and D and epsilon 0 are fixed, but AR 6 times higher, therefore CF 6 times CI. So going back to a red pen and substituting our values now for delta E, we can say delta E is a half times 7.6 times 10 to the minus 10 all squared, multiplied by 1 over 6 times, now pico is 10 to the minus 12, so 63 times 10 to the minus 12, take away 1 over 63 times 10 to the minus 12. And when you bung all that lot into your calculator, you will get 3.78 times 10 to the minus 10 joules. And of course, it's actually going to come out on your calculator as negative. Now, since we're interested in the change, we can effectively just ignore the sign, and the mark scheme says just allow negative or positive answers. In the next part of this question, you can see that we have what they're calling a variable capacitor. Well, it is a variable capacitor. So as you turn this spindle round here, like that, so this set of plates there moves out from the other set of plates, therefore decreasing the area of plates that are in contact with each other, and therefore decreasing the amount of capacitance. So the question is how does this area here vary as we increase the size of theta there? So I did this, thought about it like this. So if you have a circle, and we just think about this circle for a moment, then we can say that the area of that circle, well, we know what the area of that circle is, don't we? It's pi r squared. Of course it is. But what about the area of the sector? Well, the sector has an area of pi r squared over theta times 360. So if theta is 180, that means we have an area of half of pi r squared. In other words, the point to bear out from this is that the area is proportional to theta. So it's a linear relationship between angle and area. Now in our case, as the angle gets bigger, so the area is going to decrease, but it's still linear. Having established that the relationship between theta and the area of the sector is kind of linear, we can now take that and apply it to our variable capacitor, noting that theta is actually the angle outside of the overlap, if you like. So we're interested in this area here. So as we turn the spindle round, then we've got to draw a graph of how the angle and capacitance changes. So when theta is 180, we're in sort of this position. So there's no overlap between the fixed plates and the rotating plates. Therefore, capacitance is 0, like that. When the angle is 0, the two plates are completely overlapping, like that. And so we're at a maximum capacitance. Now 360 degrees will be equivalent to a complete turn. So again, we're going to be at the maximum. And as we said, there's a linear relationship between theta and A. In other words, we will get a graph that goes like that. 0 at 180 and straight lines going up to maximums at 0 and 360 degrees. In this last part of the question, we need to get the same maximum capacitance, but the plates have half the diameter. Well, we know that the area of the plates over the distance of the plates, E0 ER, equals the capacitance. So if we half the diameter, what happens to the area of the plates? Well, pi r squared. So if we half the diameter, we're half in the radius. So in other words, that means that the capacitance has dropped by a factor of 4. So a couple of things we could do then. We could decrease the separation between the plates by a factor of 4. So we could reduce D down times 4. Might be a bit difficult to do, but nevertheless we could do that. Or we could increase the value of the dielectric by putting in a dielectric which has a value of ER equal to 4. And I think that's pretty well it. Well, I hope it's useful for you. Don't forget to subscribe if you haven't. Please subscribe. Thank you very much and goodbye.